quick introduction. I'm the founder and chief technologist for Apertus Solutions, and the intention for my talk today is to hit a few security concepts. That's the basis upon what TrenchBoot's going to be building on. Introduce TrenchBoot itself, kind of talk about what I'm working on currently underneath the project, and then have a short discussion over the whole thing. So the security concepts. I have several slides here. I'm going to try to go through these fairly quickly so we can get through the entire presentation. So, but I'm open to taking questions along the way if there's any. So trust. We've been hearing a lot about trust today. Trust is the basis for a lot of things, and we want to be able to trust that our system came up in a good state. So if you look at the definition of trust, there's two key words that I want to pull out of there. There's assured and strength. And when you think about this, if in a simple mathematical relationship, trust is directly proportional to the assurance of strength you have in that. And then the way you can make assurance about strength is you got to reduce the skepticism. What is questionable about it? The less skepticism you have about something, the more you know you can trust in it. So along those lines of strength, one of the topics I want to really build on is strength of mechanism. So there's a couple definitions here for strength of mechanism. A pretty early one and then a later one that was revised. For me, the key thing that I like to think about is it's an assessment of how well we can reduce the skepticism in a mechanism of whether it will fail if there's a direct or indirect force. And I say it that way. There's a couple ways you can see in the definition as explained, but the indirect force is one of the more critical ones that we know what direct force is. Somebody's attacking it, but indirect force can happen in a few ways. Power glitches is one. Right? Power glitch could be an intentional or an unintentional event, but it's still an indirection of force that you need to be thinking about when you're looking at your mechanisms. So root of trust. So we saw this term earlier today. A root of trust is really just a mechanism. That's the way I like to think about it. It's just a mechanism, and if you look at a definition of a mechanism, it's something that just achieves a result. And when you're achieving that result, when you're using that as a root of trust, that is your trust anchor. You're trusting that that result happened in the way you were expected. And then when you look at the degree of skepticism about whether that mechanism accomplished that, that is going to impart what your strength of mechanism is. So when you start building your systems, you need to really be thinking about looking at the mechanisms you're relying on to establish your trust in the system and how strong, how resilient are they against both direct and indirect application of force. So now that we know what a root of trust is, the question becomes, where is that trust rooted? Where are you rooting that trust in? Where is that mechanism implemented? Is it a hardware-based? So is that mechanism something that your hardware is doing, or is it something that's actually being done by software? I tend to find that this kind of gets confused sometimes. Some people tend to think that they have a hardware root of trust when they're a little bit more in software. But the key point here is that you understand that when you implement in hardware, the ability to apply force to it is going to be more difficult. So that's why we tend to impart higher strength and hardware roots of trust as opposed to software roots of trust. So now that we know what a root of trust is, the fact is that many of our systems are made up of multiple roots of trust. TCG has these three standard ones they like to talk about, and when it comes to the specifications they've developed. I've got another slide of them. I'm not going to go through each and every one of these, but it's good to understand that there is multiple roots of trust in your system, and each one of these can be rooted in hardware or software, and they're going to impart a strength of your total system. So root of trust for verification is a good one to be mindful of. We'll get into that one in a moment. So now that you know about these roots of trust, here's a simple view into the interactions of how these roots of trust may work inside your system. So you have a root of trust of measurement, and it's responsible for taking measurements about your system and storing those measurements in your root of trust of storage. And as I note here that you can have multiple roots of trust for storage in your system. You can have ones that are storing measurements and one that are storing your keys. If you're doing a root of trust for verification, a key-based verification model. So that's where you get into the root of trust for verification. That would be retrieving your keys from your root of trust for storage. And then to be able to make integrity statements about this entire system, you rely on a root of trust for reporting that can give you guarantees about how it can read those measurements and present them to you in a manner that's not tampered. So now that we've gone over what a root of trust is, some basic interactions between them, you have measured root of trust systems. This is what a lot of people will refer to as a measured launch or a measured boot. So you have a root of trust measurement mechanism. Typically, it's a cryptographic hash, and the very first measurement that's taken by this system is what's referred to as your core root of trust for measurement, your CRTM. And whatever it's calculating, whatever the mechanism that does that initial calculation, that is your root of trust. That is what you're relying on, that it made that measurement the correct way, and it makes it the same way every time. And then you have your root of trust to storage and root of trust for reporting. And these typically are implemented with a TPM. I'm not going to dive into all of the properties of the TPM, but basically the TPM guarantees that you can put measurements into it, and those measurements will not be tampered with easily. I will say it that way. And then it has a key hierarchy that allows you to then have some confidence that the measurements that it reported out came from that TPM. So you have a verified root of trust types of systems as well. So these are what you're a verified boot, or sometimes referred to as a secure boot. In this system, you're going to have a root of trust for verification. This is your signature system. This is your public key stored and used to verify the signature of a boot ROM. The implementation of this is typically in software. So your root of trust here is actually software-based. And the strength of this root of trust is going to be driven by how well you know that that verification process cannot be subverted when it executes. And then root of trust for storage. So there's in a verified system, especially in the modern UEFI systems, you'll have two. You have the one that's storing your keys for verification, and you'll have one that's storing measurements, because measurements will be taken later after you verified the system as what you expect it to be. Typically, you see the root of storage being flash. They can be SMM protected flash is what you typically see in modern day UEFI systems. But the strength here is driven by how well you can ensure that nobody can write to that. And this brings in a good point when you're talking about this, is that you also have to think about from a software versus hardware, or physical, remote versus physical touch here, because if it's a flash ROM, somebody could, if you got physical access, somebody can just clip right on and rewrite this stuff. Root of trust for reporting. As I said, typically these systems, modern UEFI systems, will establish measurements. They use the TPM to store those measurements and then report those measurements later on. Transitive trust. Transitive trust, I like to think of it as a mechanism similar to a root of trust, because it is doing a similar action as what your root of trust is doing. It is a mechanism that is allowing you to extend your trust boundary beyond whatever you initially started with. It is a process that will verify certain properties for you to ensure that the next function, the secondary or auxiliary entity that you're going to allow to take over execution, meets the properties that you need to allow it to have control. So again, this is something that you need to think about in terms of strength of mechanism of how strong that verification is doing. And typically you'll see these verifications come in multiple forms. I got a couple here, and each one has a varying strength, right? There's a blind trust, right? A blind transitive trust. And in that case, you just say if it wound up executing, that means it must have passed the verification phase, and therefore it was good. There is no evidence base. And so in these situations, you have very little trust that you can really instill in it, because you don't know, you don't have any evidence to prove that it actually accomplished it. And then you have measurement-based. So at this point, you can collect a measurement-based transitive trust will collect evidence and hold that evidence and report on that evidence that the extension of the trust was done in a manner that you wanted it to be done. Attestation. So when you've done all of this and you have measurements and evidence about how you've established your trust and you built up a trust chain and you've reached a final execution state, attestation is a means by which you can then project or ask to be appraised about your system and whether or not you're in an expected state. These appraisals can happen on device or off device, and appraisals can come in multiple forms. It can be as simple as doing a key unseal, which is what we do in OpenXT currently, or it can be a more advanced situation where off-platform quotes are sent for verification and decisions are made based on that. When you do attestation, you should make sure your assertions are rooted in your root of trust for reporting. So in this case, typically TPMs are your more common way of doing that, so you rely on your TPM to generate your quotes. And then, yeah, it allows for the verification of the validity of your trust chain, as I said. Not really a security concept, but just a basic concept that has already been discussed, so I don't need to spend a lot of time on it. But there's two ways that a platform could be launched. You can do a static launch, which is your typical power's been applied, the system's coming up. And you can do a dynamic launch, which in which case the CPU can be instructed to reset itself to effectively as if it did come out of a power on or a reset state. All right, so with all that, kind of a quick landscape slide I have here. So I like to think of these things as all boot integrity technologies or bits. These are a lot of the technologies we have out here today that you might come across that allows you to instill, build up roots of trust and integrity about a system when it's being booted. The only one I would really take a moment to speak to is a hardware-assisted boot. That's a overloaded term, but it's the best one I could come up for. This is things that are going to be like DICE, Cerberus by Microsoft, these types of devices that help ensure the integrity of the system before the CPU is given access. All right, so any questions on all that? I went through that a lot faster than I expected, so everybody good on trust? All right. TrenchBoot. So TrenchBoot, the objective behind it is I want to build a uniform cross-platform framework that a system builder can pull into their system and build security engines that incorporate these specific bits that you have available to you. And you can build secure systems using the bits for your implementation. So where did this all come from? So in 2015, I started working on the measured launch capability of OpenXT. Specifically, I was looking at a problem called forward SIL, in which case I was actually, when a system needed to update, we needed to be able to have the environment unlock itself after the update, even though the PCR values would have changed. When I was doing this, I found myself constrained in retrofitting to a highly coupled solution. I was able to decouple it some, and that's not meant to be as derogatory towards OpenXT. The problem with a lot of these technologies, they tend to, these integrity technologies tend to turn into tightly coupled solutions, just because of what you're trying to do to enforce the integrity. One of the things that happens with that is that the integrity itself was limited or brittle. So the platform could only boot into the state that it was sealed to. Any deviation in startup, valid deviations such as setting a debug flag or something like that, would cause the system to be considered unknown. There are a variety of other reasons. And so I wanted to be able to deal with variations in the boot process. And have the system be able to react accordingly. And then the solution was constrained to TXT platforms. vPro is typically only found in enterprise class devices, so not as prolific as just your general PC. So long-term goals of what I want to try to accomplish with TrenchBoot. So as I said, I want to build this common framework that allows purpose-driven security engines to be built. And provide abstractions. The framework will be able to provide you abstractions from the bits so that a common set of security actions could be taken regardless of which bit was used to start the system. And then be able to provide the ability to configure a sequence of security actions depending on what happened and what was measured. And then to ease the building of this, I want to leverage the open embedded build system, which is demonstrable at providing configurable and reproducible builds and provide support for a variety of use cases. One of the ancillary goals out of this is to build up a source of ground truth out of all of this. Today, when we look at TPM measurements from a system boot, we just have to trust that the ASCII or the BIOS measurements are what they're supposed to be. We have no source of where those measurements came from, whether they're valid or not. We just know that they were the ones that were there when we sealed the system or made whatever integrity setup with those measurements. So one of the things I want to do is try to start crowdsourcing a lot of these and try to collect a database of these BIOS measurements so that and provide them in a public attestation service so that people could then start verifying whether their box that they received really is running the firmware that it's reporting it is running. So from a general architecture, this is effectively what I'm trying to build up. So, and the areas that work will be done in. So there might be some bit augmentation that might need to be done to add additional capabilities. And then the pieces that will build up the security engine. So we'll have the bit ingestions, we'll have security processing, and ways to launch follow-on solutions. And from that, the idea is that then using open embedded and a properly set up config file, each of these pieces could then be put together in a means that is capable of launching the platform, your target platform. All right, so the current effort. So what am I working on with my spare time? I am building an embedded AMD OpenXT server. I am demonstrating using an AMD late launch implementation that I'm working on to build what I'm calling my new measured secure boot to launch OpenXT. It consists of a PC Engine's APU2, which is an embedded AMD processor, single board computer that I wired a TPM12 onto. I'm in the process of writing a Grub late launch relocator so that a way I can actually spawn an SK init from Grub to a target secure loader, which is the next phase that I will get to, which is to actually take Linux boot / uroot security engine and late launch into a Linux kernel that will be running an augmented uroot system that will take care of the security aspects that I want to do. And then from there, that will be able to launch OpenXT in a secure manner. So my new approach to secure boot. So traditionally, secure boot is thought of as like a verification measurement attestation sequence. Ownership in this thing is passed by blind delegation, and what I mean by that is if you're familiar with the UEFI key store, anybody with physical access can then re-provision those keys, and questionably whether or not they could actually do it remotely. And there is no good way of detecting key tampering, depending on if the person did it well enough. So one of the things I wanted to do with this is actually invert this a little bit. So I want to take a measurement of the verification system and do that in hardware so that way the measurement could not be tampered with when it's done. And then I can do a verification-based system in which anybody, the ownership can be passed to anybody by just reprovisioning the box with your own keys in the loader. one of the nice things that this does is that the delegated key is measured and stored by hardware, and you have almost unlimited revocation of key. So to explain AMD SKINIT a little bit, what I'm using for the late launch, so SKINIT is in every AMD V supported processor. And one of the things that I've found beneficial for this is that unlike AMD or Intel's TXT, AMD left the secure loader as an exercise for the implementer. So what that means is that the only thing required by SKINIT besides setting up the CPU environment is that your loader just has an offset and a length at the beginning, and your blob is within 64K. So that means that SL header that they call out there is implementation specific. You can put anything in there. And then one of the other things is that even though in designing it, they were thinking that the hashed measurement would be the entirety of the code and static data, it doesn't have to be. It's just going to hash whatever that length value is set to. So what I'm going to do is I'm going to leverage that to put the public key inside of the, as effectively the header, and then have the hash be everything up to the image signature. So at that point, what I will be able to do is when I do an SKINIT and launch into this loader, the hash the measurement calculated by the CPU at launch time should match what's in the image signature that's been signed by the public key or by the private key of the public key that's in this loader. So what this winds up doing is you have a root of trust for measurement and root of trust for reporting truly rooted in hardware through the SKINIT and TPM. And then you have a root trust for verification and root trust for storage. The key storage is contained within the CRTM measurement. So you have integrity about that key that you can then use to verify the signature of the rest of your stack all the way up through. So just a quick recap of the benefits of this approach is that compared to the verify measure, we can the CRTM is nearly impossible to subvert. You have a strong ownership of the key without the need of a blind trust. And as I pointed out, you have a strong and flexible key management process. You can now provision your boxes either with a per device key or you can actually provision it with an enterprise key. And you can revoke any of these by effectively just zeroing the key out. And even though I'm using AMD to do this, there's actually the approach itself is a generic approach and could be actually used on multiple platforms, including Intel-based platforms, if so chosen. So with that, are there any questions? Yes?
One of the thing. And first question, have you seen Matthew Garrett work related to TPM posted last year? And how this, if you've seen how this applies to your work?
So you're talking about the boot guard verification? The boot guard verification?
Because, I'm thinking about Matthew Garrett's patches posted for Grub. They were posted last year, as I remember.
Yes. So, so he's asking about Matthew Garrett's verification or measurement patches to Grub. I wouldn't.
It was based, as I remember, on TrenchBoot project or something like that. Yes, I am familiar with it. So he wanted to introduce taking measurements by Grub when it was launched via UEFI. So his implementation was specifically UEFI bound because he was leveraging the UEFI's TPM functions as opposed to putting something into Grub. Yeah, the only thing he was doing there was he was just extending. So the way that measurement framework worked inside of Grub is that anytime a Grub command or a Grub action was taken, that would get hashed as well as whatever was being loaded and to be executed. So I would say it would be complementary. That would be, so if you think about that, if you're familiar with Grub, all of that effort would be right before the relocator. So his patches could be applied to Grub that I was, to my version of Grub, or the Grub with my patches on it, and he would take all the measurements of everything Grub did and have those stored in PCR 7 and 8, I believe it's the ones that he used, and then SKINIT would fire off, and then you would get PCR measurements for 17, and then whatever the SL loader would, whatever we did inside the SL loader.
Okay, so at some point I would like that you review his process before merging them into GraphQL. Are you okay with that?
I have looked at them. Yeah, I mean.
We merged these patches, we will go to merge these patches in the second half of this year. So I will say see you on this process, and I would like to get your opinion.
Okay, we can talk afterwards about it.
Another thing, are you going to upstream all this work we are discussing?
I'd like to.
I'm happy to see your process in upstream.
So I would like to. I would actually, so right now, I have very little spare time that I get to spend on this as it is. But when I do, so one of the other things that I want to do is I want to do a Grub relocator for TXT.
Okay.
And so then you could have a Grub EFI module that would be able to late launch into your target environment if you had a landing zone for it, in Intel's terms in MLE and AMD terms in SL. Yes?
So I'm curious, you mentioned that you're using Linux boot in your slides.
Yeah, well.
How does that come in if you're also, like, are you using Grub to load Linux, or is Linux actually?
So yeah, just 1 second, I'm getting dry. So one of the things I didn't highlight in there, I talked about the SL loader, or the secure loader. What I will be doing is, you're familiar with Linux boot, right? So it's just basically a special built Linux kernel that you incorporate the uroot system into it, right? I'm going to be patching the Linux kernel, so if you're familiar with the boot structure of Linux, there's that lower bit that used to be the real mode code base. Luckily it's 64K. So I'm going to slap my secure loader right in there and use that to DMAR protect the Linux kernel environment that we just launched into, and then basically do a few more setup things and then hand over control to the Linux kernel. Yes, sir.
How does TrenchBoot constrain SMM during the ERTM process?
Constrain SMM. So SMM is a challenge, right? There's going to be a really good talk tomorrow afternoon about some work with SMM. When TXT and SKINIT, the SEnter instruction and SKINIT instruction fire off, at that point, all interrupts have been disabled, so SMM can't really tamper with the instruction itself. As soon as it exits, it could start tampering with the environment. Before it enters, it could tamper with the environment, but during that instruction execution, it can't. And it's in that time frame where you're, I'm not as familiar with TXT as I'd like to be, because a lot of that stuff's handled by what's handled by the ACM versus what's being handled inside the SEnter instruction. But I'm pretty sure that at least the first measurement into 17 in TXT should be done by the CPU. It is done by SKINIT. So SKINIT, the only measurement it takes is the CRTM for your secure loader, and that's stored in the 17. So that first measurement is free, as far as I'm aware of tampering from SMM. And because it's stored in your root of trust for storage and reporting, again, it's outside of the control of SMM. Now, after that, can it subvert your attestation process and things like that? Yeah, those are going to be challenges you have to deal with. So, does that answer your question? Okay. Yes, sir.
So you mentioned that this approach is applicable to other platforms other than AMD.
Mm-hmm.
Because there is an equivalent of SKINIT in other platforms.
So there's my vision of ways it could be done. So obviously you could do the TXT from Intel, boot guard. So instead of doing boot guard verification, do boot guard measurement. So boot guard has the measurement mode. All you need to do is do boot guard measurement mode and make sure that your keys are inside that firmware load, and you've effectively recreated this exact situation. And now you've routed your UEFI keys into hardware via boot guard. As much as boot guard could be considered hardware rooted.
Is there anything similar in ARM world?
Yes. So some ARM process that I'm aware of, you can actually the first stage bootloader can be flashed directly into the chip, and if you implemented a measurement scheme inside of that, if you're generally those are produced by the manufacturer of that chip. If you can convince the manufacturer of that chip to write you a first stage loader that will do a measurement for you, and you know for certain that flash can never be rewritten after manufacturing, then you've now rooted into hardware a measurement. Am I out of time? All right. One more question. Yes?
Maybe this question will be answered by others. In TrenchBoot, what environment are you running in where you can run kind of middle layer services like Attestation? So is it Linux at that point, or is it just a custom?
Yes. So in the first reference platform that I'm building, which is the AMD platform, yeah, it is that Linux and InitRAMFS uroot environment. So I don't know if you're familiar with uroot. Okay. So I'm basically writing, I did this with the measured launch capability I originally did. I created a PCR calculator that allows me to do, mimic the PCR calculations and everything and reads all the data and all that stuff. I'm re-implementing it to Go, and I'll submit it for upstream to uroot if they'll take it. But all of that's, okay. So all of these security actions that I want to implement, I want to implement them inside the uroot system, and upstream them so everybody can use them, and that way I don't have to maintain them as much, right? And that's where the open embedded build system would kick in, because then it could just pull the upstream uroot system as it builds your security engine for you. Okay.
So I want to make a comment, which is Daniel's trying to do something that on paper would be either impossible or unwise, because the vendors would say, well, how can you have one universal approach? But I think what Daniel brings to the table is a depth of experience and a willingness to consider all the options. So what I think needs to happen is everyone who wants to work on this should not look at his code, should try to read the docs, do it themselves, submit their patches to him so he can review it, and then hash it out. And that way we're going to educate another pool of secure boot DRTM literate developers to advance the state of the art, including changing the hardware and changing AMD and Intel. And John McCune's in the audience, who explained to Intel and AMD in a paper years ago how to fix the performance problem so we can do this at runtime instead of only at boot. So there's just to be done, which is well understood, but we need more people to help
Yeah.
the folks trying to tackle it.
Yeah, I mean, one of the unstated goals of this, or indirect goals of this, is that myself and several people in this room, we have the knowledge and understanding of how a lot of this stuff is supposed to work and how we should be able to build these systems securely. But there are system builders who don't really grasp all of this low level. What is trust? How well can I trust this and everything else? So at the end of the day, when if TrenchBoot is really successful, they won't really need to know, right? They can go, all of it will be documented on the site, so they can go read and understand. They can then, that will guide their selection and what parts of TrenchBoot they build, and be able to incorporate that system. And then that way we can start having more secure systems that have a trusted foundation on them.
Yeah, and so the next two talks, coincidentally, are from OEMs who are working in this area. We're very happy that Dell and HP are here, but clearly we need more OEMs to participate and have their developers acquire the skills to help out.
All right. Thank you.